Okay. So let's continue our discussion about this problem of finding minimum and second minimum in an array. Uh, so we had seen one algorithm. So this was the algorithm, the first algorithm we saw. So we first of all we just compare a1 and a2 and decide whichever is smaller, and depending on that we set up min1 and min2. So min1 and min2 are here two variables, and so min1 is storing the current minimum and min2 is supposed to store the current second minimum, right? And then you go from I equal to 3 to n, and you check AI, and accordingly you update your min1 and min2, right? By comparing AI with your min1 and min2, you decide on that whether you need to update or not. Okay, so that's the algorithm we saw, and what we observed was that in some cases we were making two comparisons in each iteration. In some cases we will make only one comparison in an iteration. So this actually basically depends on the input order, right? So for some input orders, we might be doing many comparisons. For some input orders, we might be doing not so many comparisons, right? Uh, right. So what do you think is the worst case input order, right? So worst case is when every iteration sees two comparisons, right? So what do you think? Can you suggest some input order which will take two comparisons in every iteration? Okay, so someone said sorted array. So sorted in which order?
Ascending order.
Okay, so let's consider an array in ascending order. So maybe let's say 10, 20, 30, 40, and so on. Um, okay, now let's see this code. When do you get into two comparisons, right? So when you go into the else condition, then you see the second comparison, right? If you go into only the if part, then there is no second comparison. So that means you go into second comparison if your ith element is greater than your current minimum, uh, right? So clearly this sorted array seems to have this property, right? Because every element is larger than the minimum seen so far, right? So every time you will go into this else case, and you will see two comparisons, right? In fact, there are more examples where you will see two comparisons in every iteration. So can you think of other examples other than this sorted array?
When all elements are equal.
Mm, yeah, yeah. This equality I could take care of just making this less than equal to, right? That would take care of it. So this equal things are not very interesting. Uh, but still, there are interesting examples where elements are distinct, need not be really sorted, but still you are making two comparisons in every round. So think of this thing here. I mean, in what kind of inputs you will get to see this most often?
So the first one should be the smallest element, and rest of them can be in an audio any order.
Right, correct, great. So if the first one is the smallest and the rest of them are in any arbitrary order, doesn't matter, right? If your array looks like this, then you will always get into this, right? Because min one will always remain here and your AIs are always greater than this. So you are always falling into the else case, right? So it looks like there are many worst case inputs, right? So you could say the worst case input is when minimum is at first position, right? So this is really the worst case. Um, if you think about it, if minimum is at the second position or third position, even that is quite bad. So it's not the worst, but it's still quite bad because as soon as you see the actual minimum, after that you will keep doing two comparisons in this, right? And can you think of a best case input? What could be the best case? So best case is when we see only one comparison in every iteration, right? So you always want to get into this if part, right? So can you think of some example?
The array is sorted in a descending order.
Right, right. So if the array is sorted in descending order, then AI will always be less than equal to the current minimum, right? So the best case looks like sorted in decreasing order. Okay. Okay. So basically, the point is that um, the number of comparisons, total number of comparisons, depend on the input order, and that's why the idea we suggested last time was that let's do a random shuffling before running our algorithm, right? So the hope is that by random shuffling, a bad input order will become a good input order with large probability, right? So of course the other way around could also happen, that good input order could become bad input order, but I'm hoping that the probability of turning into a bad input order is low somehow. That's the hope, at least. So we still need to see whether that's happening or not, right? So any questions?
So can you repeat it, please?
Which part? Which part do you want me to repeat?
Yeah, the best case input. Actually, I just joined late, so
Okay. Uh, so basically, we saw this algorithm, which sometimes, so in in every iteration, either it makes two comparisons or one comparison. And we were looking at best case input order and worst case input order. So, uh, what is the best case input order? Best case input order is when AI is always less than the current minimum, right? In that case, you make only one comparison. So that
okay, sir.
happens when your array is sorted in decreasing order, right? Because if it's
Thank you.
sorted in decreasing order, AI is always less than the current minimum. Okay. Okay. So any questions about this random shuffling? What is the hope? Yeah. So I just want to emphasize one more point that I mean the point of random shuffling is that I don't want to assume anything about the input order, right? So it is possible that the somehow input is coming from some source where we are always getting a bad input order, right? So when I don't have any guarantees on the input order, it's a good idea to just randomly shuffle it and then hope for the best, right? That's the idea. Okay. So
So, so
yeah, go ahead.
this randomly shuffled sequence means the input order. Every
Hmm.
input order will have equal probability of occurring. No? Or we
Right,
are assuming that the best good input order will occur with a large probability or something.
right. So yeah, the comment was that when we randomly shuffle, every input order will be equally likely. Yeah, that is correct. So how do we know that good input orders come with large probability? We don't know it yet. We still need to figure it out, right? So it's true that every input order is equally likely. The only question is how many input orders are good and how many input orders are bad. That's what we need to figure out. Okay, so let's see it more closely. Uh, so let's focus on the ith iteration, right? Just focus on the ith iteration. So as we already discussed in the ith iteration, the good event is when AI is less than equal to minimum, current minimum, and the bad event is when AI is actually greater than the current minimum, right? Because then you see two comparisons. So let's write it. So good event is when AI is less than equal to current min, and bad event is the other case. Uh, so which of these two you think is more likely? So just focus on the ith iteration. So out of these two, which seems more likely? So you see, suppose, so by the way, is it clear why is it this good event and why is this a bad event? So any questions about that?
The bad event seems more likely
Bad event seems more likely. Why? Why?
because in for the good event to be true, the input has to be in a decreasing order. Whereas for a bad event, if only the first element is a minimum, the rest can be anything. So
Right,
it has
correct.
a large number of permutations.
Right. So yeah, so indeed it's true that the bad event seems more likely. So let's see just in the ith iteration. So suppose so far the I minus one elements, let's say they are arranged like this, and the minimum is somewhere here, right? Minimum is sitting here. Now the AI, the ith element comes, and what is the good event? The good events that is that it falls here, right? So that is the good event. It falls somewhere below the minimum. And what is the bad event? Bad event is that it falls anywhere here, right? So it seems like it's much more likely that it will fall into this range above the minimum, right? So that seems much more likely. Uh, so does that sound reasonable? So is everyone convinced that the bad event seems more likely here?
Sir, could you repeat this once again?
Okay, so is it clear what is a good event and what is a bad event?
No, sir. That's a doubt.
Yeah. So now what we are saying that good event is when AI falls below the current minimum, right? So suppose this is my current set of elements, right? These are the first I minus one elements. And what is the good event? The good event is that AI falls below the current minimum, right? So it has to follow somewhere below this line. And what is the bad event is when it is anywhere in this range, right? Anywhere above the minimum one, right? So if our if we think of the first I elements as uniformly permuted, right? So if every permutation is equally likely, then what is the probability that AI will fall below the current minimum? So in fact, I'm asking what is the probability that AI is the minimum among first I elements? So that seems very low probability event, right? That should happen something with probability 1 by I. So my guess is that probability of the good event is something like 1 by I, because I want the ith element to be the minimum among the first I, right? So that seems very less likely. And that's why I'm saying the bad event is more likely. Um, okay, so I hope it makes sense. So we are doing something wrong here. We need to change something, right? So can we change our algorithm some way, in some way, so that the opposite happens, right? So we want what we want is that the possibility of two comparisons become less likely and possibility of one comparisons become more likely in every iteration. So can you change this algorithm somehow? So we are doing something wrong here. So we are comparing AI with the current minimum, uh, and then depending on that we are doing something. So can you suggest some other strategy?
You can compare AI with min 2, and if it's great.
Right, right,
Yeah,
great. So okay, so here is the suggestion. So suppose this is the current set of elements, and the suggestion is that the new element, suppose this is a new element, we should compare it with first with second minimum, and depending on um, the result we should do something, right? So suppose AI is greater than the current minimum, the second minimum. So let's say AI is greater than min 2. Okay. So then what happens?
Then
Yeah.
again, we
Can
need to check one more time with minimum one. AI.
no, if AI is greater than min 2, that means AI lies somewhere here,
Yes, sir, sorry. Yes. When we then we don't need to check it with min
we
one.
can ignore it.
right? So that's the good case actually. So then we don't need to do anything. So if AI is greater than min 2, then we don't need to update our min 1 and min 2, right? So we don't need to do anything here. So that's like the good case, right? And suppose that's not true. Suppose AI is less than min 2, right? So that means AI could be here or it could be here. We don't know where, but it's somewhere below min 2. So in that case, what should we do? Anyone?
Compare it with min 1, and if it's less than min 1, uh, then change it to min 1, and min 1 should be assigned to min
Right, right, right. Yeah. So if AI is less than min 2, then the next thing we should check is whether it's compare it with min 1, right? So if it is, let's say, greater than min 1, so that means it lies here, right? So if AI is here, then I just need to update my min 2, right? So min 1 remains same, so I just update min 2 equal to AI. Okay, and else means what? Else means that AI is here somewhere. right? So it's below everything. So in that case, we need to update everything. So we need to update min1 is now AI. So AI is our new minimum one, and for min2 we need to write the
Min2 would
current
be
minimum.
assigned first. Min2 would be assigned first, min1
Right,
second.
right, right. Yeah,
Sir,
so I always make this mistake. Yeah, yeah. So I should update min2 first because, right. So does that make sense, everyone? Any questions about this new algorithm? Okay. Okay, so now the algorithms looks in a good shape, right? So in the ith iteration, if AI falls in this range, right, above minimum 2, that looks like the good case for us, right? Because we are doing nothing in that case. And it does seem like this is more likely, right? So if every permutation is equally likely, then it's more likely that AI will fall somewhere here in this long range, right? Compared to somewhere below the min 2 range, right? So looks like our algorithm should do good. Okay. So now let's try to formally analyze this algorithm. Okay. So any questions before we do that?
Sir, I am worried about the initialization of min1 and min2.
Okay. So initialize is the same, right? So I did not write the initialization here, but it should be the same what we did here. So just compare element 1 and 2 and just update min1 and min2 accordingly, right? That's what you do, initialize.
So what if A2 is the biggest element in the array?
So I mean, if A2 is the biggest element, in the beginning it will become min2. And okay, I guess you are talking about, okay, the question is what if A2, the second element is the largest? So that means we will always fall into the else case, right? And that means we will always make two comparisons, right? So this is like the worst case, right? So you're right that this kind of input will be the worst case, and basically we have to figure out the exact probabilities, right? So with what probability we are getting into a good case and with what probability we are getting into a bad case, right? So that's what we want to analyze next.
So how is A2 like once we see A3 then
Hmm.
we will should change A2, right? So how is A2 being largest the worst case?
Oh, right, right, right. You are right. So yeah, it doesn't make sense. Yeah. So I take it back. So A2 being largest is not the worst case. Sorry. Uh, so what would be really the worst case for this algorithm? I guess I want AI to be always less than min 2. Yeah, so if it's decreasing, yeah, if it's in decreasing order, then it's the worst case. Yeah, but that's not very, I mean, that's very low probability event, right? 1 by n factorial. Yeah. So anyways, I think we can say something with certainty when we do a close analysis, right? So let's,
sir, I didn't understand what he meant by changing it to. Can you please repeat that?
by changing, so the latest comment you mean?
Yeah, yeah, yeah.
Yeah.
Can you
Yeah, so the
explain that?
latest, yeah, so. we were wondering about this condition. What if A2 is the largest element? And I was afraid that when A2 is the largest, then every time you will get into else case. But
Right.
that's not really true
Why
because
so?
um, see, I mean, we are comparing AI with the current second minimum, right? So if A2 is the largest, it doesn't matter, right? I mean, AI will be compared with the current second minimum,
I see,
and
which will get updated.
yeah, so current second minimum will keep getting updated,
Yeah.
and
Yeah. Got it. Yeah.
yeah.
But in that case also it will enter the second condition, right? So there will be two comparisons.
Well, it depends on your current second minimum, right? If your current second minimum somehow gets updated to a very small value, then I guess you are in a good shape. Yeah. Okay. So I think we should try to formally analyze this. Okay. So what I want to do is I want to compute the expected number of total comparisons, right? Um, so I guess so far it's clear to you that the minimum number of total comparisons is somewhere around n, right? I think n minus 1 maybe. And the maximum number of total comparisons is um, I think somewhere around 2n. So it's probably 2n minus 3. Okay. So don't pay too much attention on this plus minus constant factors. Uh, okay, so the question is now, can we compute the expected number of total comparisons, right? And that will give us a good idea about the performance of this algorithm, right? So yeah, so let me first define formally what I mean by expected number, right? So for any random variable x, so clearly our number of total comparisons is a random variable, right? So it takes different values with different probabilities. So I mean, it takes different values with certain probabilities. So it's clearly a random variable. It's not a deterministic variable. And whenever a variable is a random variable, we talk about its expectation, and it's defined like this. It's defined to be summation over all possible values for this variable x. Then you take that value, you multiply with probability x equal to x. Okay, so that is the definition. And yes, it's some kind of probabilistic average, right? So that's what we call as the expected value of a random variable. And that's what we want to estimate for the total number of comparisons. So any questions about this definition? Okay, so let's write this. So let's say x is the total number of comparisons, right? So it's a random variable. So we can write its expectation like this, that so we know that its range is from its possible values for total number of comparisons. It goes from somewhere around n minus 1 to 2n minus 3, right? So that's what I have written here. So I'm taking a summation over all possible values for x, and maybe I'm not very precise here. So let me just write x from n minus 1 to 2n, and so I will go over all these possible values. I will take this sum, and the value x times the probability that I'm making exactly x comparisons, right? So that is the expectation formula. Okay. Um, so what is this probability here? Uh, so you know that each each input order, each permutation is equally likely, right? So each input order has probability 1 by n factorial. So this probability is nothing but number of input orders which will see exactly x comparisons, right? And you divide it by n factorial, right? So that is the probability. So does that make sense? Okay, so so any ideas on how we can estimate this or how we can compute this? So you have so many input orders. Now we want to figure out uh, how many input orders see exactly X comparisons in total over the course of the algorithm. So any ideas on how we can find out this number?
Sir, inversion
Yeah.
pairs?
Mm, version pairs. I'm not. I know. I don't understand. What do you mean by that? Are you suggesting an algorithm to compute this?
Um, I mean, my hunch was that since the descending order gives the worst case possible, maybe
Hmm.
for each count of inversion pairs, like we can find out the number of
Hmm.
permutations with those number of inversion pairs. And
Okay. 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 So the suggestion is that. So first of all, what is an inversion pair? So I think by inversion pair, it is meant that um, so the number of pairs such that the larger element of the pair comes first and the smaller comes second. So for example, if you have something like this, then 5 4 is an inversion pair and 5 3 is an inversion pair and 4 3 is also an inversion pair, right? So the suggestion is that somehow if we count the number of input orders with exactly X inversion pairs or something like that,
yeah,
that
something on
should,
those lines.
yeah, but see the number of inversion pairs, the range goes up to n choose 2, right? There could be up to n choose 2 inversion pairs.
Yeah,
Yeah, so I think we need to make a more precise statement here because the range of X here is only goes up to 2n.
all
Yeah,
right.
so we can't really say that. So maybe I guess still it's possible that you can make some connection with number of inversion pairs. But then the question will again come that how many permutations are there with those many exactly inversion pairs? And I'm not sure if that's easy to compute or if there is a simple formula for it.
Okay, sir, I'll
Mm,
think about this
yeah,
later.
yeah. So yeah, one needs to think about it. So any other ideas?
Number of rearrangements
Number of
permutations, rearrangements.
dearrangements. So that
Yeah.
means so dearrangements. I guess you mean that uh,
Combinations.
uh, uh, some number is not sitting at its right place. I guess that's what you mean.
Yeah. Yes.
Yeah. So you want to count all permutation where exactly k of the elements are sitting at the right places. Right places meaning they are sitting at exactly what their rank is.
Yeah.
Okay, I'm not sure if that will be helpful here. So all these are interesting ideas, and I think one needs to think about it, whether it's really helpful in computing this. And my guess is that my guess is that it's not helpful. Okay. And I also need to think about it, but that's my first guess that these things might not be helpful. Um, so, I mean, do you see some concrete connection why it can be helpful, or it's just a
Yeah,
guess?
like it seems like so the problem is similar, like putting uh, the deer elements and this one.
Okay, so yeah, we can think about it that can we connect this number of input orders with exactly X comparisons with the number of input orders with exactly X elements sitting at the right place.
Yeah,
Okay. Yeah. So let's think about it offline maybe. I'm not sure if it's really connected. So any other ideas on this? So to me it looks difficult to find this. So you can think about it, and if you have good ideas about how to estimate it, we can discuss it offline. Uh, right. So by the way, this expression is same as oh, so can you still see my slides?
Yes, sir.
Yeah. Yeah. So this expression is same as this other expression I'm writing here. So this is summation or all permutation. Each permutation is equally likely 1 by n factorial. And then how many comparisons you are making in that particular permutation sigma. Okay. Um, so you can verify that these two formulas are actually the same, equal to each other, and that's what we're trying to estimate. And yeah, this second formula also doesn't look very helpful. I mean, I can't really go over all permutation and for each permutation estimate this. I mean, from computational point of view, clearly the first formula looks more helpful, but even there, it's not really clear how to estimate. Okay, okay, so what I want to do is I want to suggest a better idea, and let's see if that makes more sense or okay. So here is my idea. So my claim is that if you want to compute expected number of total comparisons, right? So the same formula, right? I'm not changing the definition. The definition remains the same. I'm just suggesting that there is a different way to compute the same quantity, right? So here is my suggestion that we go over all iterations, and in each iteration we compute the expected number of comparisons, right? So from I equal to 3 to n, you so this is my loop over all iterations, and in each iteration let's compute the expected number of comparisons, and then add all of them, right? Let's add all these numbers for each iteration, and I'm saying that that should give you the correct answer. And maybe you need to do a 1 plus 1 because of the initialization, right? So yeah, that's not really important. Okay. um so does it make sense? I mean, does it look like an obvious statement which you knew in class 2 or something? Or does it look like a non-trivial statement? Any comments on this?
Sir, like,
Hmm.
is this because of linearity of expectation, right?
Right, right, correct. Yeah, so I'm not sure if everyone has familiar with linearity of expectation, but this is not an obvious statement. I mean, it's not very hard to prove. If you think about it, you can figure it out, but it's not an obvious statement. So, I mean, what is obvious is this. So you can always say that the number of total comparisons. So let me just copy this. So if from this equation, if you remove this expectation part, so if you remove the expectation part, then its equation is clearly obvious, right? Because number of total comparisons is simply summation over all iterations, and you add up the number of comparisons in each iteration. So of course, the left hand side is a random variable and the right hand side is also a random variable, but this equation is always true, right? And so this is obvious. And by linearity of expectation, you could say that if okay, so let me write what is linearity of expectation. So linearity of expectation says that uh, if you have a random variable x, which is a sum of some other random variables, summation xi from I equal to whatever. Um, so if this is true, then you can apply the same equation on the expectations also. Okay, so that's what this linearity of expectation theorem says. So this is a theorem and you should be able to prove this easily. I mean, if you think about it. Okay, so that's what the theorem. So in our case, what is x and what is xi? X is the total number of comparisons and xi is the comparisons in iteration I, right? So that's what I'm applying here, and that's how I wrote this claim. Okay, so any questions?
In the theorem which you wrote, x and xi are both random variables, right?
Right, correct. X and xi are both random variables, right? Yeah, but the point is that in this equation holds no matter what. I mean, this equation is always true. This equation is not random. I mean, and this equation is true with probability 1. I mean, that's the point. And that's why you can apply expectation on this equation.
Okay, sir, understood.
Okay. Any other questions?
So when you say am I audible?
Yeah, yeah.
And so when you say expected number of comparison in iteration I, you
Hmm.
mean like for all permutations in iteration I, or you mean for one particular permutation?
No, no, very good question. So when I say expected number of comparisons in a iteration I, maybe I should write what I mean by that. So, I mean, yeah, that just means that you look at all possible orders, right? So each comes with probability 1 by n factorial, and over all these possibilities, what is the expected number of comparisons in a particular iteration I? That's what I mean.
Okay, sir.
Okay, so yeah. So maybe let me write it. So basically expectation xi is okay. So one way to write is that you go over all permutation. Each permutation has uh, probability 1 by n factorial, and then you say um, the number of comparisons in iteration I on order sigma, right? So for this particular order, if you go into this particular order and you see the iteration I, how many comparisons are there, and then multiply by 1 by n factorial and sum over all orders. So that is what I mean by expectation of xi, right? And there is another way to write it, right? In terms of the possible values xi takes. So another way to write expectation of xi is, so what are the possible values for xi?
0, 1, and 2.
Okay, is 0 really possible?
No, sorry. 1 and 2.
Right? So if we go to this iteration, so one comparison you anyways have to make. Possibly you can make a second comparison and that's it. Right? So we can say that xi is either 1 or it's either 2. Right? So the expectation of xi can be written as 1 times probability of xi equal to 1 and 2 times probability of xi equal to 2. Right? And that's what, I mean, that's why I wanted to focus on a particular iteration, but because uh, now it looks much more manageable, right? So now I don't have to think about maybe all permutation orders, but it looks somewhat simpler, right? So, and clearly um, because 1 and 2 are the only possibilities, if I sum up these two probabilities, the sum is 1. So I just need to find one of these probabilities, right? So either find the probability of xi equal to 1 or find the probability of xi equal to 2. So now that is the only question. So let's find out. So by the way, so far any questions about this formula, this equation?
Sir, one question. So we
Hmm,
have written number of comparison on iteration I on order sigma,
right.
right? So this
Yeah.
we are calculating for one particular order only.
Yes, I mean that is the in the definition. The definition is like this that uh, you go over all orders so that this summation is n factorial orders. And then for each order, you look at the comparisons in iteration I, you add them up, divide by n factorial. That is one definition. And I'm saying this is exactly same as this expression below. And maybe it's not immediately clear. So you should think about it, that these two things are exactly equal. So here I'm saying that 1 times the probability of xi equal to 1 and 2 times probability of xi equal to 2. And I mean the important thing is that when I say probability, this probability is taken over all possible orderings, right? So we know that each ordering is equally likely, and this probability is, when I say probability of xi equal to 2, that means that I consider all possible orders, and among them, how many orders will have xi equal to 2, and with using that, I get this probability. Okay. So does that make sense? Any questions? Okay. Any other questions? Anyone? Okay. So now we have one task left, which is to compute this probability xi equal to 1. Probability of xi equal to 1. Or let's say, let's go for probability of xi equal to 2. Right. So how to compute that? Okay. So can we write this xi equal to 2 in terms of AI, right? What should be true about AI for this condition to be for xi equal to 2?
Yeah, less
Minimum
than equal.
among
Right. So AI must be less than the second minimum, right? So if we go back to the algorithm, the two, you make two comparisons in the else case, and the else case means AI is less than equal to second minimum, right? So let's write this. So AI is less than second minimum of what? Second minimum of A 1 till I minus 1, right? So the elements seen so far, right? So whatever elements you have seen so far, what is the second minimum and what is the probability that AI is less than that second minimum? Okay. So any ideas how to compute this probability?
The 2 by
Hmm.
I plus 1.
I think you mean 2 by I, because we are looking at the ith, right?
If it is, what if it is larger than the largest seen so far?
So you meant plus 1 here?
Yeah, yeah, yeah.
No, no. I think it should be something like 2 by I, because there are only I elements, right? Including this AI, we have only I elements so far.
Oh,
Yeah.
oh, right, right,
So
right. Oh, yeah, yeah, yeah. Sorry, sorry, sorry. Yeah.
yeah, right.
I,
So yeah, can you explain how did you get 2 by I?
yes, so basically there are I positions in which you can place place the element that is coming, but only two
Right,
of those positions are favorable for this probability. The
right,
like the first one and the one above that.
right. Great, right. Yeah. So the important thing to notice here is that, see, we know that each permutation is equally likely, right? So each order is equally likely. It also means that each order, so if you fix the first I elements, right? So suppose these are my I elements, and consider the event where the set of I elements is fixed, right? So even those sets, even within that set, each of the I factorial permutations are equally likely, right? So each order of this subset A1 to AI, right? That is also equally likely with probability I factorial, A1 by I factorial, right? Um, so the point is that, what do I want? I want AI to be somewhere here, right? So AI to be either at this position or at this position, right? So these are my first I elements. So suppose these are my first I elements, and what is my favorable condition? Favorable condition is AI is less than the second minimum of 1 to I minus 1. So which is same as, so let me write it in other words. This is same as probability of AI uh, being either the min or the second min among the first I elements, right? So that is what we are looking for. Okay. And yeah, so because every permutation of these I elements is equally likely, what is the probability that AI will be minimum or second minimum, right? It will be 2 by I, because every element is equally likely to be at the ith position, right? So every element is equally likely to be at the ith position. What is the probability that minimum or second minimum will be at the ith position? So that probability is 2 by I. Okay. So yeah, we'll continue this argument, and we'll finish the analysis next time. So any questions about this number 2 by I?
So here we only took that each order of a of 1 to I is equally likely, but we did not consider. I'm not sure where we considered the fact that each order from 1 to n is equally likely.
Right. So, I mean, see, what am I saying here? I'm saying that what is my good event? The good event is that the minimum or the second minimum among the first I lands up in the ith position, right? So, there are different ways to think about it. So, maybe for some it is easier to focus on the first I elements and then think that each I factorial permutations of those I elements is equally likely. That's one way to think about it. If you don't want to think like that, it's fine. You can also think that each n factorial orders are equally likely, and then the probability that the minimum or the second minimum among the first I lands up at the ith position, that is 2 by I. Yeah, I mean, I'm not doing it very formally. Maybe I will just write it in the notes very formally, but I hope intuitively it's clear how we are getting to by I. So any questions? Okay, so I guess I will write down a formal proof for this probability in the slides, and then you can read up that formal proof, yeah, if you are interested. And yeah, so
I wanted to ask, is there a difference between expected running time and the average running time that we compute?
okay, so the question is there a difference between expected running time and average running time? So I mean, I defined what is expected running time. You will have to define what is average running time. So what is your definition for average running time?
So, like in algorithms, we always find that theta bond, right? That what it is average state behavior is. So there is a difference in
No, this
randomization.
okay. So I'm not able to hear you properly, but this theta notation has nothing to do with average running time.
Okay.
Yeah, yeah, I mean think about it. How will you define average running time? And I think if you try to define average running time, you will land up on the same definition, right? So I guess there is really no other definition for average running time than expected running time. Okay, any other questions?